X's go to the right, Y's go to the left, right? But today I'm not going to say that because it's not always going to be X and Y, right? So what I'm going to say is independent variable goes to the right, dependent goes to the left, okay? That's what I'm going to say today because it's not going to be X and Y. This is the only problem where you're going to have an X and Y, okay? So when we separate, right? dy over dx equals k times y. Multiply both sides by dx. Divide both sides by y, just like we did all last week. So then you get 1 over y dy equals k times dx. So k can stay on the right or it can move to the left. It's a number, it's a value, right? It's like pi or e, it's a number, k is not a variable. So I just leave it on the right side just because it was already there. Can you divide? So could I have divided both sides by ky and then this would be 1 over ky? Sure. But then k becomes a fraction. If it's not a fraction, why change it? Okay. Second step after that was antiderivative of both sides. What's the antiderivative of 1 over y?
Natural log.
Natural log of y, right? We put the bars because anything I plug in for y has to be positive. If it's not positive, that's what the bars are there for. Okay? What's the derivative, or antiderivative, sorry, what's the integral or antiderivative of k? Kx, right? It's on the right side, so it's going to be x. It's kx, and then you need a plus c, right? Because anytime we do integration without bounds, it needs a c. And then there was a point, we'd plug it in, right? This one, there is no point. So we got to go to the next step. The next step is solve for y, right? So how do I solve for y? We did this last week. So really, this is log base of y. That's what natural log means, right? And however you do it, whatever method you use to change this to an exponent, you're going to have e to the kx plus c equals y. Yeah, this is 100%. The nice thing about this is they always start this way. So we don't have to do this from now on because they're always going to start this way.
Perfect.
It won't be x and y, but we can, so you can do this for I'm telling you right now, you're going to have to do this for every single problem. Or you don't have to because I know this relationship. Okay? So we get y equals, e plus c. Okay? So I'm going to change this, though. The reason I'm going to change it up a little bit is because one of these is a constant, because we had a constant to begin with, right?
Oh, yeah.
So you can rewrite this as this, right? That's exponent rules.
Yeah.
This guy here is a constant. It's not a variable. This is a constant. So what they call that guy is capital C. Sometimes they'll use the letter capital C, and you're like, where does that come from? That's where it comes from. So if you put e to the c on paper, it's not wrong, but you're going to see this a lot. You're going to see capital C, and you're like, where did capital C come from? Well, that's where it came from. It's the constant part. Okay? So that's just pretty much review of what we did last week. That's exactly what we did last week. Separate and solve. Okay? From now on, the problems are going to be in context. Like the first one talks about bacteria, right? There's going to be no X, there's going to be no Y, there's going to be none of that, right? So we have to kind of define it. All right, so let's look at example number 2. So it says bacteria in a culture increased from 400 to 1,603 hours. Okay? Assuming that the rate of increase of the population is directly proportional to the population. So this is the giveaway here. This part here, is a giveaway that it's exponential growth and decay. So anytime you see that directly proportional on any problem, it means you're going to do what we're doing today. So if you're on the test in a few weeks, not this week, but the next week when we take the test, and you're like, is this one exponential growth? Okay, well, does it say directly proportional? If it does, then it is. If it doesn't, it's something else. Okay, so that's kind of the key phrase to look for. Okay, so and then find an appropriate equation. So it wants us to do what we did for the first problem. Okay, so the first thing is, they don't have any x and y's. I don't see any x and y's anywhere. Okay, I don't see any variables anywhere. So we have to determine what's the independent and what's the dependent. So read question, the first two sentences, or not even a sentence and a half, because that's before the comma. What's the independent and what's the dependent? Or what are our two variables here? What are our two variables that were, let's start there.
The bacteria.
Bacteria is one of them.
And the time.
And the time, right? Bacteria and time. The amount of bacteria and the time, right, in hours. Which of those is independent and which of them is dependent?
Independence out.
Yeah, usually I would say 99 out of 100 times, time is going to be your independent. Okay? Independent. So we'll call that T for time. So that means bacteria, number of bacteria, is going to be the dependent. We'll call that capital B for bacteria. Now you can call those X and Y. Instead of T, you can use X, and instead of dependent, you can use Y. But then you're going to have to always go back and say, what was X again? What was Y again? So that's why I use letters that are closer to them. Can you use X and Y instead? Yeah, but when you're answering the questions, it makes it a little more difficult because you keep forgetting which one's X and which one's Y. Okay? Okay, so here we go. We are going to set up this guy here using the letters that we have. So what is ours going to be? It's not going to be dy over dx. K is the only thing that's going to change. The equal sign and K are the only thing that's going to stay. So for this problem, what are we going to have on the left side? D what over D what? D capital B over dt equals K times what? Capital B. Okay, because Y is the dependent, sorry. All right, so we get D capital B over dt equals K times capital B. Looks familiar, except no X and Y's, T and a B. But it's going to be the same thing. Our first step is going to be the same thing. I'm going to do the first step over again, but you don't have to do this over again because it's going to be the same thing as number one, just instead of X and Y, you're going to have T's and B's. Okay? So we would say, who's going to go to the right and who's going to go to the left? Are the T's going to move to the right or the T's going to move to the left? T's to the right, B's to the left. So we're going to multiply both sides by dt and divide by b. Okay, so we get 1 over capital B dB equals K dt. Now let's try this. Let's try this and see if we're ready for it. After we do integration, right? That's our next step. Our next step is to do integration. Integration. What are we going to end up with? If you can't see, it's okay. But I just want to see if we're ready to skip that step. Natural log of B, good. Natural log of B equals, keep going. KT, keep going, plus C, good. And what are we going to end up with afterwards? B equals capital C times e to the KT. That's what we're going to use. Okay. That's the generic. That's the generic or the general solution. They want us to find one that is appropriate for this guy, right? Okay, so it's a good place. Like I said, remember the difference between the general solution and the particular solution? So this is the general solution. We need to tailor it to this problem here. Okay? So how do we do that? Well, we use what we know. I know a couple things about this guy. I know that time, there was 400 bacteria, and then 3 hours later there was 1,600 or 1,600 bacteria, right? What times were those? At what time was there 400 bacteria? Initial, right? Initial. 3 hours later, there was 16, right? And that's all I know. I don't know how much it was growing after that. I don't know if there's a pattern. I think it's exponential, but I'm not sure. All right. So what I'm going to do is I'm going to use those to create the particular solution. Okay, I'm going to use those. Here's the thing. Capital C is always the initial amount or the starting amount, right? So the starting amount or initial amount, it's always going to be that. That's what always going to be. Always, always, always capital C. And we know that already, right? 400. So let's rewrite it. B equals 400 times E to the KT. Okay. Okay. So now what I got to do is B and T are our variables, right? So we're not going to, those are going to stay B and T. What we have to figure out is what that constant is. What is K? What is K for this problem? Okay. So to do that, this is exactly what we're doing in Math 3 actually right now. It's funny that we're doing this exact same thing. We're not using calculus to solve, but we're using algebra to solve. But this is essentially, I did a problem exactly like this about bacteria. I just didn't use calculus to solve it when I was doing it for Math 3. But so you guys have had a little experience with this in exponentials. So we're going to use what we have, what we know, right? I know that at time 0, there was 400 bacteria. And at time 3 hours, there was 1,600 bacteria. My model has to equal that. So when I plug in 3 for T, I better get 1,600 for B. And when I plug in 0 for T, I better get 400 bacteria. Well, we already know one of them. If I plug in 0 for T, you're just going to get e to the 0. E to the 0 is 1. So we know that one. So we're not going to use that one. I'm going to use the next one. I'm going to use the one right below it. I'm going to use this guy right here. Because that is what it should be. When I plug in 3 for T, it better equal 1,600 for K. Or for B. Okay? So let's see. 1,600 equals 400 times E to the 3K. So when my Math 3 students do it, they approximate this. We're actually going to figure out what it is, okay? Because to get the correct answer, you have to use calculus. To get an approximate answer, there's other ways to do it, but we got to solve for K. What's the first thing I got to do to solve for K? Get it by itself. So what are we going to do first? Divide by 400. Yep, divide both sides by 400. Good. Now, luckily, this will give us a nice, clean 4, right? It won't always be that way. But for this one, it's a nice, clean 4. You might have a fraction, you might have a decimal. Okay? So that leaves E to the 3K. How do I get that K down to the ground? Have to use a logarithm. Yep, the only way to get a power to the ground, to the floor, is to use a logarithm. Okay, so I'm going to write it. I'm going to flip it around. I'm going to go over here real quick. Oops. The easiest way. The easiest way to change this to a logarithm is what I call the L, kind of like the loop, except it's the other way because you're trying to make it into a log instead of getting rid of the log. So this is what I do. I'll show you what I do. If it works for you, that's great. If it doesn't. So you take the log of e, so that becomes a natural log, right? Okay. The natural log of 4 equals the power, 3k. How do I solve for k? Divide by 3. So you can divide by 3 or you can put 1/3. Up to you. So my last step is put that back into the one I kind of started here. B and T, we don't know. It changes on every problem. They're variables. Variables change on every problem, right? K will not change because it's not a variable. K will always be 1/3 natural log of 4. So we get B equals 400 times E. K now is 1/3 natural log of 4 times T. This is the model, what we call the model, another fancy word for an equation, that we're going to use to solve this problem. We're going to use it to solve B in a second. That's the hard part. Once you do that, the rest is not very hard. Okay? Yeah, so the next one, what are we going to do? What do you think we're going to do to solve for at the end of 6 hours?
Plug in 6.
Plug in 6 for T, yeah. Plug in 6 for T.
400.
So B equals 400
Natural log of 4.
times 6. So yeah, calculator. If you've never used the NumWorks calculators, or I'll show you how to do it right now.
Yeah.
There we go. Okay, so we just want the calculation. We don't need the graph right now. We just need calculation, so hit enter. So we got 400 times E. E is right above sign, right below shift to the left, top left corner. We want the power of 1/3. So we go, I usually put parentheses when I do powers. You don't have to, but I usually do parentheses just so that I don't, I keep everything organized, kind of keeps everything organized. Times natural log. Natural log is right next to the E. To the right of the E, ln. 4. It's already a positive number, so I don't need to change it to positive. If it was -4, you'd have to change it to +4. But since it already was positive, we're going to leave it like that. Times 6. Close parentheses, enter. If you get a decimal, they'll tell you how to round it, but it's not a decimal, you can see. So we're good, 6,400. So the number of bacteria after 6 hours, 6,400. Okay. So once you create the model, answering the questions is a lot easier. The hardest part about it, or I don't want to say hardest, the most difficult, the most complex part of it is finding the model. Okay, so here we go. Radium-226, it's an I don't think radium's an element, or radium-226, so radium is an element, but this is the 226, okay? So it's a particle, whatever, I don't know the exact words of it, but loses its mass. So it loses its mass at a rate directly proportional. So on the test, that means we do what we've been doing, right? To its mass. So its mass is how much is left. How much of it is left. Usually grams is usually, or milligrams is usually how they determine how it's left. If it's half-life, what is a half-life?
Half-life is how long it takes for it to become half its original.
Yeah, like half-life is pretty self-explanatory, but you would be surprised at how many people don't know what a half-life is, even when I say half-life. So that means its half-life is 1,590 years. So that means in 1,590 years, it'll have lost half of its value, right? So how much does it have right now? 100 milligrams, okay? So that means in 1,590 years, it's going to have half, okay? All right, so the first thing we got to do is, what's our independent? What's our dependent?
Independent's probably our half-life, no, because that's just time.
Okay, so we got time. So time in years, right?
Yeah.
Okay, so that'll be, like I said, 99.9% of the time, years is going to be your independent. Okay, so independent, call that T.
Okay.
What is going to be your dependent, or the Y? Milligrams, yeah. Grams, mass, measured in milligrams, yep. Okay. Right, that's your dependent. So when I'm doing this, I usually don't like to use, so like you're like, why don't you use milligrams? I don't like to use more than one letter. I used to like to use one letter. So I'm not going to put mg because when I'm doing this, there's enough letters that we use. Why do I want to make another one? So what could I use instead of mg? M for mass, right? I can use M. I can use capital R for radium. Either of those is okay, right? M, I don't want to use lowercase m because that means slope. So capital M for mass, totally okay. Capital R for radium, totally okay. Okay? And this is one of the reasons I do it, so whoever's reading my problem, they know what I'm using. What does M mean, capital M mean? Shows, okay? Okay, so here we go. So let's set it up. Look on the very first page. What is it going to be? What is it going to say? What is it going to say?
D capital M over dt equals k times capital M.
Perfect. Perfect. Mm-hmm. D capital M over d lowercase t equals k times capital M. Okay. So here's the place where you can save some time. What is it going to equal? I'll give you a hint. It's going to be m equals something. Say it again? Capital C, keep going.
E to the power of kn.
KT.
Sorry.
There you go. Okay.
Sorry.
You can do that. It's okay. We've done it in our notes. You know, it's the same thing over and over again with different letters, right? So I don't mind that. Save yourself some time. Okay. Capital C we know is a starting amount, right? So what is this going to be? Do they tell us a starting amount for this guy? They do. What's the starting amount?
100.
100. So they want a formula. Again, formula is a less fancy word, but it's the same thing as model. Okay? So we need to find k, right? K is always, for this situation, k is always going to be the same. T and m are going to change depending on time and depending on time, it's going to change. Okay? So I always make a little table. That's what I do to organize my kind of what's given. So we have T and capital M. The initial was 100, right? So the initial was 100. What else do we know?
After 1590 years, it'll be 50.
And then another 1590, it's going to be 25. And then another, you could keep going, but I think that's good for right now. We get the idea, right? Every 1,590 years, there's going to be half left over. You just need one besides the initial to get the ball rolling. Okay. So here we go. I'm going to use this guy here.
Not 25.
Half-life.
So M, capital M was 50. 100. E to the 1,590K.
Oh no.
Okay, we got to solve for K. Get K by itself. Isolate it, right? So what's the first step to isolate? Divide by 100. So you can leave it as 1/2. You can change it to 0.5. It doesn't matter. It doesn't matter what. I usually leave it as a fraction because sometimes decimal, I don't know why. I just leave it as a fraction. Do you have to? No. You can change it to 0.5. If you want to do 0.5, go for it. Okay. Let's see. E to the 1,950 or 1,590K. So if we can do this in our head. What is K? So on one side you're going to get 1,590K, right?
Yeah.
What is that going to be equal to?
Natural log of 1/2.
Natural log of 1/2. Good. If you're not sure, mentally I just did the kind of did this. Natural log of E. Natural log 1/2 equals that. Divide by 1,590. So we get K equals 1 over 1,590 times natural log 1/2. Put that back in. E to the, natural 1 over 1,590 times natural log to the 1/2 times T. That's our formula we're going to use for the problems. What do you think we're going to do to find B?
In our heads, calculator.
Well, you could use calculator, but what do you think we're going to do?
Plug in 1,000 to T.
Plug in 1,000 to T. It's already in years, so plug in 1,000 for T. It looks super complicated, but your calculator is the one that has to do the heavy lifting. So
Tragic.
times 1,000.
Even though it's not half-life, so.
So it doesn't say how to round, but I went 3 spaces. So I got 64 point. Yeah.
Whoa. What a.
Is that the number you guys got?
Yeah.
Okay. Good. Now, always do a common sense check. Does that number fit? So if I were to put that in the table, if I were to put this into the table, would it make sense and would it fit the pattern? If I were to put this number in the table here, would it make sense in the table?
maybe not the rounded version. That's like you would need to put like a little.
So 64.66. What years would go with it? 1,000. Does that make sense that that number is about 64 or 65? Yeah, because it fits right in between, right? Closer to this guy. All right, so yeah, that's the common sense. If you got something like 200.9 or something like that, then you know, whoa, how did it go up? It should be going down, right? So that's kind of the common sense thing. Okay.
That's the answer. That's the answer. Find it.
All right, so here we go.
Uh-oh.
Next question. When will the mass be reduced to 30 milligrams? So do I just put 30 for T and I calculate it, right? No. So they kind of change it on you guys. I'll show you how to do it. There's a couple different ways you can do it on the calculator. Okay. So now milligrams is 30. So 30 equals this guy here. 100 e to the 1/1590 times natural log of 1/2 times t.
Hang on, wait, where is it? What is this variable?
So now we got to solve for t. Okay. So kind of like we did earlier with k, because t is up in the sky. We did with k, we got to do the same thing, right? So divide both sides by 100. 30 hundredths is 0.3 or 1/3, or sorry, 3/10. And then you get e to the 1/590 times natural log 1/2 times t. How do we get something? How do we get a variable down to the or exponent down to the ground? By using a log, right? In this case, it's going to be a natural log because it's got e. Yeah. Okay. So it's going to be natural log of 3/10 equals the power. It's not as bad as you think because the calculator is going to do the hard part in a second.
Luckily, do you multiply by, wait. We're gonna multiply.
And then what are you going to do now? How do I get t by itself? Divide. Divide by everything. I don't want to stay on that side. I don't want this guy to stay.
You're all multiplying the fraction. Can you be dividing it by
I know roughly what to do, bro. This is.
What a beautiful home.
Yes.
You gonna lie?
So you're going to go to your calculator and you're going to calculate that. Make it look exactly like that in your calculator.
Natural log of 3/10.
Make it look exactly like that in your calculator. Calculator can do it. It can handle it.
Oh, 50.
It's going to be a decimal.
I kind of.
No, actually, yeah, it'll be a decimal.
I can't.
It'll be like 2,761 and change.
Oh my. Yeah.
Oh, no, I just canceled everything. Well, that was the wrong number.
Okay. So watch, I'll show you. Let me see here. Okay, here we go. So we have natural log of 3/10 or 0.3. So we have, usually I do division first because it's going to be, or actually no, I don't want to do division first. Natural log of 3/10 or 0.3, however you wrote it,
That's incorrect.
divided by 1/1590 times the natural log of 1/2.
Hey, my pencil. I want a pencil.
There you go.
calculator.
You wouldn't
Appreciate it.
usually be like,
Oh, that's pretty.
775,
My
yeah.
new favorite company.
775. Okay. So yeah, the hardest part about today is the first part. If you get the model down, if you get the formula down, you just plug it in the calculator afterwards. Okay? All right, so for number 4, do A for me. 4A. It's about a manufacturing company determines.
Is it in months? Okay. Unit under capital U.
A manufacturing company determines.
Right, so U is.
So you see it doesn't say directly proportional, but it says was proportional. That's your key that we're going to use exponential growth and decay.
So 5,000. Units. U, I'll stick U.
So I used S for sales and T for months for time. Do you have to use those? No. You don't have to use T and S. You can use X and Y if you want.
He's missing a Y. He's missing a
I use capital U though.
Okay, buddy. Zip it. I did the exact same. I also use capital U.
Oh, wait, me too.
No, I gotta change it.
Why you gotta change it?
Alright, so 5,000 equals, okay, so 7,000 equals 500 times DKT. 5. Hang on, wait. 705. 705 equals 3. Equals E3K. 7,000 equals 5,000 times E3K. So, alright, so it's U equals 1/3